Right. Okay, good. So it's recording. Yeah. Okay. So one of the most original oxidizing agents developed over all time was basically Jones reagent, which is a mixture of either chromium trioxide or the dichromate. When you mix it with sulfuric acid, you form the chromic acid, which is a really strong oxidizing agent. The second one, which was developed a bit later on, is just a mixture of chromium trioxide, pyridine, and hydrochloric acid. And so the pyridine and the hydrochloric acid, it's just a buffer. It just buffers the reaction. So a lot of compounds that are sensitive to acid, if you threw in Jones reagent's going to destroy it because it's got HCl in it. So these are the two oxidizing agents that are discussed in textbooks the most. And as I said last class, the chromium's toxic too, so that's another disadvantage to the whole using chromium. Now, how does this actually work? So the simplest way to do this is let's use a so the simplest way to do this, let's use the PCC type variety of things. So, and I'm just going to use chromium, the chromium trioxide as the way that this is going to go. Okay, so we've got the oxygen is going to complex with the chromium. Some electrons are going to move up. This is going to form now we've got a system like this. There's going to be what we call a proton transfer step. This happens very fast. And so and I'm going to draw it like this. RC. Nope. And now we've got something that looks like this. Now the last step is basically it's very similar to an E2 type elimination. The difference is that the leaving group isn't anything we've seen before. It is it's going to be the whole chromium species. But the proton that we want to remove is this proton right here. So we would just use, actually, if we use pyridine or any Lewis base, because sometimes there's water in the mixture too, so you could use water as your Lewis base on this one as well. We're going to grab that proton. These electrons are going to go here, and these electrons are going to go onto the chromium. So we will form our ketone. And then chromium now is going to look like this. So overall, your chromium has been, it started out as chromium trioxide. Now you'll notice that there's no longer 5 bonds to chromium. There's no longer 6 bonds between chromium and oxygen. There's only 5. So the chromium, which is the oxidizing agent, has been effectively reduced. And you'll notice that these little electrons here are moving onto the chromium. So they're gaining electrons, so they're going to be, technically a reduction of that metal. So that's basically how this works. So it's an E2 elimination of that chromium species after you've made the oxygen chromium bond. So you can do the same sort of thing with the chromic acid or the dichromate. You're going to end up with a structure that looks like this. Anyway, so now the interesting thing is that, I'll just put a little break here, is that for ketones, for secondary alcohols, let's draw a whole bunch of secondary alcohols. Oh, what's another secondary alcohol? Let's do this. It doesn't matter if you use Jones reagents or PCC. And I'll put PCC, dichloromethane here. The product is always going to end up being a ketone. So we will oxidize these bonds. So what was once a carbon oxygen single bond is going to become a carbon oxygen double bond. So with ketones, it's relatively straightforward. With primary alcohols, however, there's a slight difference between the two. So, so if this is for secondary alcohols. Now with primary, the two reagents work slightly differently. So let's do this. And let's do this. Actually, let's do this. Let's do exactly the same one. This is PCC. So Jones, it's a mixture of basically 3 things. You've got your chromium trioxide, some source of H+, sulfuric acid, water, and acetone to solubilize everything. So chromium trioxide or chromium, the dichromate. So that's basically what Jones is. With PCC, it's chromium trioxide, HCl, and pyridine. And we're going to dissolve it in dichloromethane. Jones will oxidize the primary alcohol all the way to the carboxylic acid. Whereas PCC is just going to oxidize it to the aldehyde. So Jones goes all the way to the carboxylic acid, and PCC stops at the aldehyde. Now, if you were to do the same reaction in PCC, but do it with, say, in the presence of water. So we add a bunch of water to it. Water is the key point here. The product you end up making is the carboxylic acid. And I'm going to basically explain how this works in a second. So the key point to the PCC oxidation is there's no water in the reaction. So some textbooks will use as a solvent DMF, which was this solvent here. We remember back from our SN2 reactions. Now, DMF is really hard to get water out of. So when you do a reaction with PCC and DMF, what this is telling you is that there's water there because it's so hard to remove. Oh, the miscibility of DMF and water is so high that it's really hard to get rid of it. So certain textbooks, depending upon what PCC is dissolved in, if it's in dichloromethane, it goes to the aldehyde. If it's in DMF, it goes to the carboxylic acid. And what it's basically saying is that with DMF, there's water associated with it. So the mechanism for this is exactly the same as it was previously. So we'll just do the mechanism again. Mechanism. So we've got chromium. So let's go there, electrons go up. We'll do a proton transfer. In fact, the solvent's got so much, if it's the Jones reagent, it's got so much acid H plus rolling around in there that this would get protonated right away anyway. So, but let's just do it like this because it's easier to see. Is that? So we make our chromium ester, our chromate ester here. And we've got 2 protons. And so this mechanism is in, let's say this is the oxidation, there's water there. Why does this go to the carboxylic acid? So the next step will be that water is going to remove that proton. We're going to do the elimination to make our aldehyde. And our reduced chromium. Now, the interesting thing, so why is water so important in this reaction, is that in the presence of, particularly in the presence of acid, this reaction is accelerated. It reaches equilibrium faster. Your aldehyde can be protonated. And what this does is that this makes our carbon here even more electrophilic, right? Because the carbonyl has got that oxygen now has a positive charge on it. So electrons are being pulled towards the oxygen even more, which makes that carbon even more electropositive. Well, water is going to come in and sense this. It's going to attack. Electrons are going to move up. And This is going to make this. You might have seen this before. And let's just remove one of those protons with some water in the solvent. All of these steps here are in equilibrium, so they're all reversible. But this type of structure is called a 1,1 diol, or it's sometimes called a hydrate, just a hydrate of a, so both ketones and aldehydes in the presence of water and acid will form these 1,1 diols. They're not, it's an equilibrium which heavily favors the ketone, or the heavily favors the, I should say, the carbonyl compound, except for some very simple aldehydes. But anyway, you form this 1,1 diol. And so the problem with this is that if you've got chromium in your reaction, once you form this 1,1 diol, what's going to happen? Well, the alcohol is going to come in and attack. The electrons are going to go up. You are going to, it's going to be the same mechanism again. We're going to do a proton transfer. Let's do this orange. Now we've got our little proton still there. And we can do our E2 elimination. And this is going to finish the oxidation. So this grabs that proton. These electrons go to make the pi bond. You eject your chromium. And voila, we have our carboxylic acid. Boom. So the key point for this second step of the oxidation is the formation of this 1,1 diol. So if your solution is in the presence of water, water is going to end up attacking that protonated carbonyl. You're going to form the 1,1 diol, and then that can be further oxidized to the carboxylic acid. So it's a so with PCC, if there's no water in the reaction, it'll stop at the aldehyde. But if you add water to it, it's going to oxidize things all the way to the end. So because Jones, the reagent itself is made, the solvent includes water, you can't avoid this over-oxidation. But with PCC, you can. So that's basically the difference between the two. The mechanism is exactly the same. The difference is that in the presence of water, you form a 1,1 diol, or sometimes the 1,1 diols are called gem diols. Gem for geminal for twins on the same carbon. So I guess that's where that comes from. So that's the oxidation reactions. There are a couple of other oxidizing agents that we've basically seen. Well, there's another one which is very similar, which is potassium permanganate. This is a very strong oxidizing agent. It basically oxidizes alkenes and it oxidizes alcohols. It can even oxidize carbon hydrogen benzylic in the benzylic position. So it oxidizes everything. So it chews things up. So it's not particularly useful. But the one reaction that it is quite useful for is that if you've got a benzylic carbon, the two H's. If you've got a benzylic carbon which has a carbon hydrogen bond, so here there's a hydrogen on the benzylic carbon, here there's two hydrogens on the benzylic carbon, here there's none. Potassium permanganate actually oxidizes this to the carboxylic acid. Oxidizes this to the carboxylic acid. Here there's no reaction, We won't deal with the actual mechanism to this, but in fact, it does a whole bunch of stuff. We're breaking both of these carbon bonds, we're breaking that bond there. As long as there's a hydrogen here, it can oxidize things all the way to the carboxylic acid. So this is technically not only, this is actually oxidizing an alkane to a carboxylic acid. The key point though is that it has to be a benzylic carbon. So if we remember, the carbon that is beside a ring, so this carbon here is the benzylic carbon. But there has to be a CH. So if there's no carbon, if there's no hydrogen there, then it doesn't work. Okay, now, don't worry, like, I'm basically telling you this if you, it's helpful in some of the synthesis questions. So it's a way of making carboxylic acids. It works very well for very simple molecules. Anything more complex with alkenes or alcohols, it's going to do a whole bunch of other side reactions. Now let's see here. So oxidations, we're still on the alcohol section. Right. I think that's basically it. I think that's the end of the alcohol chapter. Did we do conversions of ROH into RBR or RCl? Have we done that yet? Using Thiol Chloride or phosphorus tribromide. I will take that as a no. So, for example, if we have and this only basically works for primary or secondary alcohols. So if we had this or this PBr3, we would make and more specifically, if we had so you can go from a primary or a secondary alcohol and make an alkyl bromide using phosphorus tribromide. This is an interesting reaction. The second part of it, going from here to here, should give you a hint as to what the mechanism is going to be. So the first step, this is actually, it's kind of strange. Okay, so let's do a little mechanism here. Let's do the first one just for the sake of clarity. Okay, so it looks like we've got two Lewis bases here. Phosphorus tribromide, all those bromines make it a better electrophile. So what's going to happen is this is going to attack. We are going to lose a bromide, and this is going to generate our active intermediate. And then this is basically going to be an SN2 reaction. So these electrons here come in and attack there. We've got our good leaving group because the oxygen's protonated, it's carrying a positive charge, so it's an excellent leaving group, and that will give us our final product. So that's interesting. So that's PBr3 plus primary or secondary alcohol will give us a alkyl bromide. So in the second step here, because this carbon's a secondary carbon, the little one I starred in pink, when the bromine comes in and attacks, because it's an SN2 reaction, SN2, we will get inversion of configuration. So that's why here this is inverted inversion. Oh, we got, okay. For whatever reason, my chat isn't flipping up and saying people are chatting. So yeah, so when I asked, have we done this before? And everyone said no. It didn't show that. So anyway, so that's, yeah, feels like a Monday for some reason. All right, now the second one was with, to make a, we'll use the same reagent or starting material. The second one is this guy. Thiol Chloride. So this is a liquid. It actually, later on in the course, we're going to see that it can convert a carboxylic acid into a acid chloride. So SOCl2. So thionyl chloride, it's a super electrophile, right? Because this sulfur is bonded to 3 electronegative groups. And so the oxygen is going to attack it. And for the sake of clarity, I'll just have the chlorine leave. And so we end up with an intermediate that's going to look very similar to what we had before in the case of the bromine. Positive. Chloride's going to then attack Am I missing something here? No, I think that's all right. Okay, this attacks here. These electrons go here. Those electrons go there. And we end up with our product, Cl, plus sulfur dioxide, which is a gas. And when the chloride comes and grabs that proton, HCl as a gas. And so when you're from an entropy standpoint, this reaction works extremely well because you're releasing these gases, which makes the reaction completely irreversible. Trouble is, sulfur dioxide isn't a friendly gas to breathe in, and neither is HCl. So it can be, you want to do this in a fume hood, and yeah, it's a bit, or what you guys did in the lab, one of the labs with the gas trap, when you did the Diels-Alder reaction, you'd want to do that because that also produced sulfur dioxide during the course of that reaction. So thionyl chloride plus, so this again would be primary or secondary alcohols because this step here is an SN2 reaction. So it only will work with primary or secondary. I think that's basically the end of the alcohol chapter, really, because so alcohols, we can make them from double bonds using the hydroboration or the oxymercuration. We can oxidize alcohols to carbonyl compounds, aldehydes, ketones, carboxylic acids. At the same time, we can make alcohols from carbonyl compounds by either reducing them with lithium aluminum hydride or using Grignard reagents. So if we were to generate a little map here, I'll just put R here like this. Make alkyl halides. SCl2, we can make alkyl chlorides. We can, if we need to, with silicon, we can protect them. Triethylamine. Oops. So aldehydes, acids, carboxylic acids, alkyl bromides, alkyl chlorides. So I'll put aldehyde slash ketone up here if our alcohol is a secondary alcohol. Silyl ethers. Flashback to last term, we can make sulfonyl sulfonates. So convert these into, so we've got a leaving group. So remember, this was the MS, the tosylate, the triflate, all of the leaving groups. So you can convert them into leaving groups. And then the other thing, which we'll talk about next class, is a bit of a flashback too. Remember, we can generate using sodium hydride and Rx, we can actually make ethers. I guess we'll do this one next, but this is SN2. So only an SN2 situation. So these are all of the reactions I can think of that we've done with alcohols. Now, to make them, remember, we could start with so this is oxymercuration. This one was the hydroboration. So we could make them from alkenes. Then we could take ketones and reduce it. We could take aldehydes and reduce them. We could take carboxylic acids and reduce them. Or we could take esters and reduce them. So there's a whole bunch of different ways. So we can make them from carbonyl compounds. Then we could also do the corresponding Grignard reaction with all of these. Oops. So R minus, so then we would have R, OH, R, oops. So there's a whole bunch of R minus, so Grignard. And if you had a carboxylic acid with R minus or an ester with R minus, these would both make tertiary alcohols. So a whole bunch of different, so reductions or Grignard reagents. So there's a whole bunch of different ways we can make them. So come from carbonyl compounds or from double bonds. So yeah, there's a bunch of things going on here now. Whole host of possible reactions. I guess there's another class of alcohol or hydroxy group that we should talk about. And then next class, we'll just start on ethers. And I guess that's the phenols. Unless there's an immediate question about, so hydroboration, remember that's BH3 with potassium hydroxide and the peroxide. Oxymercuration, that's the mercury diacetate, followed by, in the presence of water, followed by the reduction with sodium borohydride. The reducing agents, remember, were either sodium borohydride or lithium aluminum hydride. Sodium borohydride was only good for ketones or aldehydes, whereas the lithium aluminum hydride was good for carboxylic acids, esters, aldehydes, or ketones. And the Grignard reagent would work on all of them. But phenols, let's just do one last little thing on phenols. So remember, a phenol is directly attached to an aromatic ring. So this makes the proton, this proton is more acidic. Than say a generic ROH. Because once you deprotonate that the electrons are delocalized within the ring. So you can stabilize them by resonance. So phenols are significantly more acidic than regular alcohol. There are a couple ways to make phenols, which we wouldn't have seen yet. So you can take either an, like say an acid, sorry, a halide, benzylic halide, and heat this, react this. This is probably completely impractical for what we would do in a university lab. Sodium hydroxide, the presence of water with a whole bunch of heat, so like 340 degrees, and pressurized 250. Second step is just adding a little bit of acid to it, and we end up making our phenol. This is through what we would call a benzyne mechanism. We'll do this later on in the class. We don't need to worry about it right now. So that's one way of doing it. Another way is what they call the Alkali Fusion variety, which is to take a sulfonic acid, use sodium hydroxide, very similar, and heat it up. And this will generate a phenol as well. Again, not particularly useful for what we would do in a lab. So for most of the time, if we're ever going to use a phenol, that will be our starting material, our phenol. Now, industrially, what's interesting is that phenols are made industrially from this guy here. So the isopropyl, basically an isopropyl benzene. This is a common sort of feedstock which comes out of the petroleum industry. So it's one of the things you find in petroleum. If you react this in the presence of oxygen and a bit of heat, this makes phenol. Plus it makes acetone. So phenols are used in like industrially they're used in a bunch of resins and this sort of thing. So it's an important building block for more complex things. Acetone, of course, is a common solvent we use for everything. So this reaction is used all the time. It's based upon, it's a radical mechanism, and oxygen has got like if you were to draw oxygen, we would draw it like Lewis structure like this, but there's a version of oxygen which it's got two radicals, and that's the reactive version which is taking place in this reaction. So it's just one of those but this is how they make it industrially. You don't need to heat it up very long, and you can just funnel it through a small sort of reaction chamber and it'll reacts. So anyway, that's basically that. Now the point that, so there's one other thing you can do with phenols, which is the point of bringing this up. And that is phenols can actually be oxidized. And they can be oxidized to a structure that looks like this. And these are benzoquinones. And benzoquinones can then be reduced to hydroquinones, which look like this. So this is an oxidation. This is a reduction. And this going back the other way would be an oxidation. So these are hydroquinones. So when you take biochem next year, you're going to hear about oxidation and reduction reactions, and you're going to hear quinones, like benzoquinones or hydroquinone type. You're going to hear about it. This is what's actually going on. It's this oxidation process here to here. This oxidation reduction process. So that's basically why I'm bringing that up, because and with enzymes and that type of stuff, these oxidations take place within the body all the time, these oxidations and reductions. But for what we do in the lab, if we want to, like synthetically, this can be is really interesting, because particularly if you start from the phenol, you'll notice that you actually add a, so if this is the yellow carbon here, you actually add and you've oxidized this other carbon too. So you've added an oxygen group specifically into that position. So it's quite a neat reaction. And then you can oxidize it to the diphenol, which would be the hydroquinone, or reduce it to the hydroquinone. So that's why I brought this up. Now, the reagent that we use to oxidize these sort of things is called Phenols salt. And the reducing agent is tin dichloride in the presence of water. We're not going to go over the mechanism of this, but if you ever need to use this in a synthesis, these would be the reagents you would use. This other oxidation here would also be with Phenols salt. And what is Phenols salt? It is this guy, SO3. Oh. But benzoyl, yeah, you'll hear about this next year in biochem. So if you ever want a mental picture of what's going on, it's this neat aromatic ring with two ketones on it, sorry, or two hydroxyl groups on it, and this other ring, which every carbon in that ring is sp2 hybridized. So it's still got that series of p orbitals that are all circular. So it's a interesting sort of little reaction. So the next thing, what we're going to do next class on Thursday is a section basically on ethers. And this isn't going to take long because we've already, we've introduced most of the things for the ethers, because we've already done all of the chemistry on epoxides, and that's a cyclic ether. And then the main reaction for the ethers, we did actually, technically we did it last term in organic 1, which was the basically one of the SN2 reactions, but we'll review that quickly. So, but the interesting thing about ethers is that they're commonly solvents. So they're solvents because they're not particularly reactive. And so there's not a whole lot of chemistry to do with ethers. So we'll do that quickly, probably just in one class. And then next week, we'll start on what we start on next week. We'll start on some of the, I guess what we should do is the pericyclic reactions. So we'll do the double bonds that are conjugated to one another, so dienes. But anyway, we'll get through ethers first. When's our next midterm?
I believe it's the 16th.
Pardon?
The 16th.
15th. Okay, so that's in 2 weeks. 2 weeks today, actually. Oh, fun. Okay, so right. Okay. All right, that's good. Okay, were there any questions on anything? So for this part about how to make phenols, that's basically if you ever need that in a synthesis type of realm. You don't really worry about the mechanism for that. Same sort of thing for the Freemy salt. But I think we basically wrapped up the alcohols. Can't think of anything else left to do with that. Okay, so on Thursday we'll do ethers, and then from that we'll go on to some pericyclic reactions, and that should be, when we get that done, that's probably all we'll get to with regard to before the next midterm, I guess. Okay, so I guess I'll see everybody on Thursday. If you have any questions, just shoot me an email. All right. Have a good day. Stay safe.
Bye.
Bye.